Hello, everyone, and welcome to day 2 of the 2024 third annual International Mars Engineering Design Competition. Today, the teams will be critiquing each other in our process of the competition. I would ask that you speak kindly to each other. Speak slowly and clearly, as some of you speak very quickly. So please try to slow down so we can all hear you well. No personal attacks on team members. I know that goes without saying, but let's keep that out of here. You have a maximum of 30 minutes total for your total critique for the teams. Please divide your critiques into divisions so that you are not going from one team to the other. So make sure you have team 1 and team 2 in your critiques, and that's all. Separately, name the team prior to your critique. So just give the team name prior to your critique. That is why it's important to put the team name in the chat so everyone remembers. If your team is being critiqued, please take notes. You will get a copy of this recording later today, but please take notes as well and pay close attention. Today is not the day for rebuttal. Today is the day for listening and taking in the information. There will be Q&A at the end only for clarification on critiques. And that will be all. So if anyone is ready, please let me know if your team is ready and we'll get started.
Hi, we're Team Aspera, and we're going to start our critique round. Next slide. So we're going to start with Team TomisMars, and then we're going to go to Team AstroMine next. Next slide. So we're going to start with critiques for TomisMars from myself, Nidhi, and Tanae. Next slide. So we're going to start with engineering. Something that we found was that you stated that Mars only receives about 43% of the sunlight Earth does, which is why we have the question, why choose solar power as the primary source while it will be very ineffective? As well as you have 90 solar panels, which will take up a lot of space and will be ineffective if covered by dirt. And then here's some information that I found to back that up with the Mars solar constant is 590 watts per meters cubed, while the Earth solar constant is 1350. And Mars only gets about half the sunlight that Earth does. And moving on to more about engineering, you stated that you wanted to use perchlorates to make solid fuel. And we found that there's not enough perchlorates to make sufficient rocket propellant, and Sabatier alternative or electrolysis is much more practical. The perchlorates are mixed and they won't be the same every time. And burn rate and symmetry are incredibly important in a solid booster. If the perchlorates aren't perfectly homogenized and a sidewall blowout is possible, which makes it very dangerous. And proper equipment needs to be there to ensure safety is really heavy. So that will add to a lot of the mass, as well as you can't really use solid fuel for anything once you get to Mars because it's rocket fuel to power rovers, vehicles, and your habitat. And some information that we found was from the 2008 Phoenix lander, which I think you guys also cited, was that there's only about 0.6 weight percentage of perchlorate in the Martian regolith. And additionally, in terms of your landing and your plan to go between Utopia Planitia and Arcadia Planitia, or vice versa, is that they're incredibly far away from each other, with I think Utopia Planitia being around 3,300 kilometers in diameter itself, and Arcadia Planitia being 2,200 kilometers in itself. And then I'll pass it over to Tanae.
Thank you, Nidhi. So we also have some other critiques on their engineering. Firstly, regarding the rover design, it appears that the maximum reach height is only 2 meters if we take their rover figure up to scale. And if the habitats figure is also to scale, this would limit the rover's ability to pile their regolith on top of the habitat module for their radiation shielding. In addition, they propose two methods for radiation shielding. As I said before, regolith piling, and the second is water shielding. Unfortunately, neither seems viable. Firstly, as I said before, the regolith piling is not feasible due to the rover's limited reach, and water shielding is quite inefficient. Secondly, water shielding is inefficient because while Deuterium Nihilus and Arcadia Planitia are optimal locations as stated in their report, if Deuterium Nihilus has less water, it could pose a challenge for adequate radiation protection. Now moving on to airlocks, having 6 of them increases the rise of depressurization events due to the large area of joints exposed to the air. This is a critical safety concern that should be addressed to ensure the crew's safety. And reducing the number of airlocks could mitigate this risk. Now, in terms of resource planning, there are several gaps in the details provided. For instance, the duration for which water will be brought is not specified, and there's no mass breakdown. Crucial life support systems such as the oxygen supply, waste management appliances do not have mass breakdowns. Also, their life support systems indicate a net loss of H2O and O2, so this is inefficient as well. They are also making methane from their life support systems, so their own life support system's purpose overtakes their overarching mission objective of creating propellant when they could have just used the methane from their life support system as propellant, which is much more efficient. Also, the habitat layout is very rigid, lacking the flexibility to adapt to unforeseen circumstances, especially in the area that they're landing in. And there's also no specified way to create the Martian fiber and no specified equipment for that, even though creating Martian fiber is listed as a mission priority. So now I'll be passing it off to Nidhi again.
So back to for human operations, the crew roles are not specified, which can lead to there being a disparity in communication or who needs to do what, as well as doesn't allow for the greater efficiency of the team. And that can also lead to disputes without clear communication and defined roles. And there is also a lack of scientific mission purpose, as it's purely for short-term fuel creating. So you could risk having your crew disengage and abandon the mission without that sense of a strong mission purpose, as well as overall loss of crew engagement through this. I'll pass it back to Tanae.
So now for the second part of their human operations, there's insufficient resource planning, and in addition to this, specifically, their bioregenerative CO2 to oxygen converter is not really specified, which is crucial for maintaining a breathable atmosphere inside of their habitat. Similarly, the food supply plan is unclear. Next, for solar panels, I did some calculations, and if we assume their greenhouse is one dome with 50 square feet, and if we use their given information for 42 watt-hour solar panels, overall you would need 115 solar panels to actually power their greenhouses, when they say they need 90 solar panels in total for their whole mission, for their whole habitat. And so this just shows that they've miscalculated the solar panels. And although the 115 solar panels that I calculated is a rough estimate, this still indicates like that they need more power to actually carry out their mission. Also, water processing is claimed through a melting oven when their tried and tested method of red water heating drill is available. Also, considering a melting oven would be largely inefficient, and they would have been fine to an extent, but since water will melt quickly, the melting ovens only for water use increase the risk of fire because they're using these melting ovens just for water melting when they could use it for other things as well. Um, okay. Now, going on to their science, as said before, their lack of science experiments is something that we do need to note. In additionally, for agriculture, a wide array of food types have been mentioned, including fish farming. And there's a stark lack of viability for fish farms, and this can be seen with the lack of equipment to process the fish for eating and life support for the fish itself. Furthermore, the mission seems to lack a focus on scientific experiments and future missions. The emphasis is primarily on making rocket propellant to return, concrete to expand the base, and fiber to reinforce it. While these are important, there should also be a focus on the longevity and sustainability of Mars missions. Understanding Mars for mass human settlement is crucial for future endeavors. Additionally, there is no mention of scouting for future missions, which is essential for the continuous exploration and understanding of Mars. This oversight could limit the potential for long-term human presence on the planet. Overall, there appears to be a mismanagement of resources and planning. The mission's design is commendable, but addressing these points could enhance safety, efficiency, and long-term viability. We believe that with some adjustments, their mission could be even more successful. In conclusion, while this design is commendable, addressing these points could enhance the mission safety and long-term viability. I will now be passing it over to Ane and Leo, who will be speaking about Team AstroMine X's design.
Thanks, Tanae and Nidhi, for that presentation about TomisMars. Okay, AstroMine's mission objective of focusing on resource extraction on Mars, while promising in terms of potential benefits, presents significant issues that need to be carefully considered. These issues span technological, environmental, and engineering challenges, as well as serious scientific and ethical concerns. Let's talk about the justification of their mission objective. They believe that the idea that an answer of no to life on Mars somehow doesn't provide a solid basis for establishing a human presence there. That's a big misconception, and I think you need to look at it from a different angle. Remember the Viking missions back in the 1970s? Those were groundbreaking. They went to Mars with a specific goal for looking for life, and at first, it seemed like they might have found something. There was a lot of excitement, but as scientists dug deeper into the data, they realized what looked like signs of life were probably just chemical reactions in the Martian soil. Now, you might think, well, that's disappointing, but it's actually incredibly valuable information. Those negative results from Viking shaped everything we've done on Mars since then. They made us think about our approach to searching for life, refining our experiments, and most importantly, they kickstarted the whole field of planetary protection. Now let's look at their main objective, the ethics of asteroid mining. Resource extraction activities from an unknown asteroid could indeed have unintended consequences on the Martian environment. Now, imagine if we start mining asteroids and inadvertently bring contaminants back to Mars. We could potentially destroy the very environment we're trying to study. Wouldn't it be a shame to put the next Martian colonies in danger and set them up for failure? Asteroid mining is a whole different ballgame with its own set of challenges. We're talking about developing new technologies for extracting resources in microgravity, dealing with the logistics of transporting materials across vast distances in space, and navigating the murky legal waters of space resource rights. Don't get me wrong, asteroid mining could be a game changer for space exploration, but it's not a replacement for scientific exploration of Mars. You need to be careful not to put all your eggs into one basket. Next slide, please, Tanae. Oh, should have talked on that slide. Next slide, please. Okay, the crew is the backbone of these missions, and their safety and well-being should be top priority. This crew composition is heavily skewed towards engineering specialties, with 4 of 6 crew members having primarily technical backgrounds. While we have a paramedic / astrobiologist, they will only have basic training, which might not be enough in the event of a life-threatening medical emergency. The poor paramedic / astrobiologist would have to juggle medical emergencies, scientific research, and mental health support, which is a lot to ask of one person and could potentially lead to burnout. Another oversight regarding the crew is that there is no clear chain of command. A mission commander is responsible for the overall success of the mission and the safety of crew and spacecraft. Without this role, the crew might struggle with decision-making and coordination, especially in emergencies resulting in a mission failure. Next slide, please. Great. The plan is to rely on a week's worth of water and oxygen until life support systems are established on Mars, which is dangerously optimistic and fails to account for the complex realities of space exploration. Setting up and validating ECLSS in the harsh Martian environment is a time-consuming process that could take months, not days. These systems require intricate integration of various subsystems for air revitalization, water recovery, waste management, and temperature control. It's not something that can be rushed or taken lightly. Moreover, the harsh Martian environment presents unique challenges that we cannot fully anticipate. Testing and validating these systems in situ would likely take far longer than a week. Any foreseen issues or delays could quickly lead to a critical shortage of essential water and oxygen, putting the crew's lives at serious risk. Remember, we're talking about human lives here. While it's admirable to push the boundaries of space exploration, we cannot afford to cut corners when it comes to crew safety. Now let's talk about water storage. Can you go back to the previous slide, Tanae? Thanks. AstroMine X's plan was to extract and store 9,000 liters of water within the first 12 days. This is ambitious and almost meets their total requirement. However, there is a catch. The stated storage capacity is only 4,000 liters, which is less than half of what they would need. This means that even if you manage to extract the 9,000 liters, where would you store it? Next slide, please. Okay, in the mission plan, AstroMine X suggests a landing site in a crater that is between 15 and 30 meters in radius. However, this is unrealistic as they are extremely rare on Mars. Most studies focus on craters that are larger than 5 kilometers in diameter, indicating that craters smaller than this are either non-existent or, more likely, undetectable with current technology. The smallest usable crater would be about 2 kilometers in diameter, with a depth of 300 meters, which is significantly larger than proposed. Second, if you're forced to set up on the open plains instead, you're dangerously exposed to dust storms. Need I remind you what happened to Opportunity rover? A dust storm ended its 14-year missions by covering its solar panels. Your power systems such as wind turbines, bioreactors, and solar panels would be toast in a dust storm. As for your long-term plans to utilize lava tubes, while intriguing, they present their own set of challenges. Finding a suitable tube in the right location with proper structural integrity will be difficult. And not to mention that most tubes are 1,000 kilometers north, well out of your rover's ranges. And your proposed in-situ construction methods are completely untested. How do you plan to maintain a stable internal environment? These are complex engineering problems that you've barely begun to address. Next slide, please. The suggestion to bring additional habitats and construction equipment for lava tube settlement would exceed the mission's weight limitations. This goes against the minimum necessary principle required for successful Mars mission designs, like Dr. Zubrin's Mars Direct approach, which emphasize bringing only the bare essentials to reduce complexity and risk. Now I'll hand the baton over to Leo, who'll be further presenting the engineering shortcomings.
The concept of redirecting an asteroid to low Martian orbit and harvesting its resources is certainly an interesting one, but by no means is it a feasible one. Team AstroMine X has stated a mass of 3 metric tons, including fuel, for their drone, the device which mines and returns the asteroid to Mars. This mass estimate has been gravely miscalculated. In fact, such a device would require over 10 million metric tons of fuel. The fuel would probably be xenon. Here's how Team Aspera calculated this volume. So for an example asteroid, we picked 4947 Ninkasi. It's quite small, 520 meters in diameter, and it grazes Mars's orbit, which means that it comes very, very close to Mars's orbit. It's fairly circular as an asteroid, and assuming 2 grams per centimeters cubed, which is the average asteroid mass, it weighs roughly 1.472 times 10 to the 11th kilograms. To the right there, or in the middle, you can see the different orbits. You can see that the light blue orbit is the asteroid's orbit, the red orbit is the Martian orbit, and the dark blue orbit is the transfer orbit. To get to Mars's orbit, it takes roughly 2,498 meters of delta V using the most efficient transfer orbit called a Hoffman, I don't know how to pronounce it, transfer orbit. 2,498 meters per second of delta V basically means they need to change the asteroid's velocity by 2,498 meters per second. Assuming an ultra-efficient electric propulsion system with exhaust velocities of 30 kilometers per second, such as those used on NASA's Dawn space probe, plugging this into the rocket equation, we get 12,889,500 tons of fuel, which obviously is well over the limits of the project. Next slide, please. Next slide, please. So the one after, oh, there, perfect. Team Aspera also believes that the masses for the rovers are very, very, very underestimated. Let's start with your exploration rover. It's got a listed mass of 20 kilograms, which is very little. For comparison, the mass of the lunar buggy, the moon buggy, the lunar exploration vehicle, is more. So the exploration vehicle obviously cannot weigh 20 kilograms, and we estimate it to weigh somewhere around 200 to 400 kilograms with or without the trailer attached. The second thing to talk about is the rescue rover, which is 4 meters by 2 meters, but it's listed as 50 kg. For reference, those dumbbells right there are 50 kilograms. This giant squid is 50 kilograms. A singular testicle of a blue whale is around 50 kilograms. So as you can see, 50 kilograms really is not that heavy. I mean, I weigh more than 50 kilograms. And so it's impossible for it to weigh only 50 kilograms. So there's 2 options. One, it's made of an ultralight material, such as cardboard, but I think we all know that cardboard can't really act as a pressure vessel, in which case it'd probably result in significant loss of life within the crew, or it's a lot heavier. We prefer to think that the crew won't die, and so we estimate a mass of at least 800 kilograms, but for such a large pressurized rover, depending on its range and power system, over 1.5 metric tons. Next slide, please. It seems like some parts of the slides are glitching out, but I'll just read it, it's fine. So the communication satellite constellation is really not very feasible. Communications equipment has yet to have been miniaturized to the same extent as imaging equipment, which is why when you look up CubeSat weights, you get really, really low weights, low masses, excuse me. But that's not the same when you look at communications satellites, not at all. So we look at a pretty light communications satellite, and really the latest that you can go and deploy in masses which is Starlink V2 Mini. This weighs around 730 kilograms. With Team AstroMine X's plan to deploy hundreds of these, I think it's quite evident how the weight of these could rack up. And the stated weight of 0.5 kilogram really isn't applicable. It could maybe be applicable if it was for an imaging satellite, but communication satellites don't scale that way. Oh, just load it in. Now, what would be a better option than having a fleet of satellites, because that provides worldwide coverage, and as far as I'm aware, your rovers don't have enough range to go across the entirety of Mars. A much better option would have a geostationary communication satellite hovering over your base, because presumably that'd be where the majority of the communications would be. While a worldwide satellite network would be useful in future missions, this is only the first mission. So really, really, really wouldn't be necessary at all. And a geostationary satellite, while not needed in and of itself, would be a much better option. Thank you.
Any other critiques from your team? Again, I'm so sorry the third team
I
is.
think we're all good.
Okay, perfect. Sorry the third team is not here. They will watch the replay for their critiques. Okay, next team, are you ready? You've had plenty of time.
Yeah, sure.
I want to mention that I participated to the Romanian national cancer competition, which I have won it, and my information based on that was used on the CubeSat system was not, in my opinion, to be considered by others, not necessarily, because it's more viable option, but I'll get that to later.
Well, congratulations on your participation. Whenever your team's ready, you may show your face or your screen and go ahead and get started.
Yeah, sure. So we are Team AstroMine, and we will start the critiques on Team Aspera.
And can I say one more thing?
Yeah.
Please speak slowly and clearly, because sometimes you talk really fast. Okay.
Okay.
Thank you.
Sorry about that.
No problem.
So we will start in alphabetical order. Yeah, I will first start with page 24. You said you will have robust medical and life support systems. I will need to ask, what do they consist of? Because other than 500 kilograms of medical instruments and a medic, I only see a third of a page of life support system. Now I will move to communication systems. I have to ask, how will the communication system work over long distances? On page 10, you said, the Beagle must be able to transport a crew of 3, along with the scientific instruments, a distance of 500 kilometers, 250 kilometers there and 200 kilometers back. So let's say you have only one medic. The medic can only be on the Beagle or in the habitat at the settlement. So if a worst case scenario happens and there is an emergency where the medic is not, what is there to do? Now I will move. No, you also said that the electrical engineer at page 4 will oversee communication systems and ensure reliable contact with Earth. Page 5, private communication channels with family and friends on Earth will be provided to maintain social connections and support mental well-being. You also said that page 7, the center of the habitat is where both central life support systems and communications is located. And the second level is where the communication systems can be found, but that's all about the communication systems. So let's say these communication systems, which I don't know anything about, they fail. Do you have a backup plan? I suppose, I don't know. Now I will go to the crew. How did you choose the engineer as the mission commander? These are hypothetical people that we are talking about. You only know their profession. You cannot choose who is the mission commander only by knowing their profession. There is not anything about the crew selection criteria. So what if the engineer is not suited to be a mission commander? What now? You will have to choose another engineer, which you may not find to be prepared for this kind of mission. Now I will go to the drill system. At page 24, you said you have a drill system of 40 kilograms. At page 1, you said craters contain ice deposits as deep as 450 meters, providing astronauts and scientists an invaluable source of study. So how could you drill with a drill system of only 40 kilograms as deep as 450 meters? What will the drill system be powered by? Now, I will go to medication and food. You will bring most of the food and the water from Earth, and you will have page 5, a small hydroponic garden will supplement the crew's diet with fresh produce. So if you bring so much food from Earth and water, have you taken into account the weight for water tanks, refrigerators? Did you take into account the power supply needed by the refrigerators? If they will get altered, you basically don't have a backup plan for food if you only have a small hydroponic garden. And I must ask, why would you use a hydroponic garden instead of an aeroponic garden, which obviously uses a lot less space? And to add, the volume of the food is way too big. Now, I will go to engineering and the power system. You said you will use a generation 4 nuclear reactor. Generation 4 nuclear reactors are estimated to be in production around the year 2030. By the year 2030, when your mission will start, our mission will be already over. Now, you said you will bring 2 kilopower modules weighing around 1,500 kilograms. The smallest Gen 4 nuclear reactor that I found is around 200 tons, called Small Seal Transportable Autonomous Reactor. And I must mention that I don't see anywhere the weight taken into account. You estimated the mass breakdown for the modules, the inflatable modules, the habitat, the human operations, the science, but nothing about engineering. And I also don't know what is the total mass of everything that we will bring. I also don't know if you will split the cargo, if we will come with all the cargo. And now there comes a bigger problem. Nuclear reactors are powered by nuclear material. Have you taken into account any kind of protection for the astronauts? Because if not, they will get cancer and they will die before they even get to Mars. And even if you bring protection, it will have volume, it will have weight, and of course, there is no such thing as 100% protection. You will never be completely safe from radioactive materials. Also, what is the cooling system for the reactors? Because we know since the atmosphere on Mars is lighter than the one on Earth, how will the heat dissipate? And you only have as a power source, you will have the nuclear reactors. Even though you have two, what if during the landing of Mars, these reactors, which are very sensible, what if they defect? What if they break down? You don't have any other type of power supply. You don't have a backup. You don't have solar panels. You don't have wind turbines. You don't have anything else. Of course. Now, you also only have one rover. The rover you estimated at about 7.5 tons. That is about a quarter of the 30 tons that you are allowed to bring. That's a lot for only one rover. What if the rover breaks on impact when you land on Mars? You don't have a rover anymore. You cannot explore as you wish. Now, at page 11, you considered sine theta as a 50-degree angle. What if the crater is more steep? You cannot get the rover out of the crater. So you only have a rover and it is unusable. You cannot move it since it has 7.5 tons. Now, you have to take into account the air composition. You calculated that you need 0.84 kilograms per day for 600 people for 300 years, to a total of 1.5 ton of oxygen brought from Earth. Have you taken into account the mass of the tank and also what is the form of the oxygen? Is it liquid? Is it gas? And yeah. At page 7, you have the mass breakdown of human operation. I want to know what kind of personal items are we talking about when you say that they will be around 300 kilos. So that means each person will bring about 50 kilos of personal items. I want to know exactly what is that. As you said, every gram counts. Also, your EVA suits, you have estimated at 1.5 ton. That means each suit is around 250 kilograms. So I really don't know how you could really do certain tasks with a suit that is so heavy, even though the gravity on Mars is way lighter, is a third of the one on Earth. It's just way too heavy. It's not a good option. Now, I must ask, you have written 30 pages. You have exceeded the limit of 25 pages by 5 pages. Out of these 30 pages, 6 pages are just bibliography. So with around 20% of the project being just bibliography, I need to ask, what is the original contribution of you to the project, or is it just a lot of information that you have accumulated from these sources? Now, my colleagues will present the critics for TomisMars' project.
Hello, my name is Teodora, and I will talk about the TomisMars project. First of all, at page 16, they state that the introduction of fish on the settlement is necessary to improve the crew's well-being and nutrition, but they will bring the fish in as first fertilized eggs, and they will be grown in a suitable water tank, which has the benefit of serving as a backup water option. My question is how will these water tanks work? How much do they weigh? And also a study at NASA showed that the muscles of the fish are basically the muscles break down in microgravity. So my question is how will they do this? Also, the same page, page 16, they stated that soil provides water retention, root support, and nutrients. What I didn't understand, we didn't understand if they misinterpreted the soil as regolith, or we didn't really understand what they were trying to say. At page 15, they made a mistake with calculating something. They stated that one human breathes 11,000 liters of air per day, of which 660 liters is oxygen, but we consume only 550 liters of it. This isn't quite accurate. On average, a person does breathe about 11,000 liters of air daily, but as air contains around 21% oxygen, which amounts to roughly 2,310 liters of oxygen, not 660 liters. Humans typically use about 4 to 5% of the oxygen they breathe in. So the actual amount of oxygen they will consume each day is closer to about 115 to 120 liters rather than 550 liters. A more accurate way to put this is that basically a human breathes about 11,000 liters of air per day, but as I said, the calculations are wrong. As a process of respirations, humans also exhale about 0.46 liters of water vapor that must be eliminated from the atmosphere and recovered for other uses. How will you do that? What is the plan to do that? Because they stated this and they didn't say with what equipment or what is the plan on doing that. At page 14, and it continues on page 15, they were talking about water recycling and that the water can be captured, filtered, and purified from human waste, sweat, and breath condensation. And our question is, how will you capture water from human waste? What, again, as I've said with the water from the respiration, with what equipment will you do that? Again, I quote from their project, for hygiene purposes, the showers and other similar facilities will be aeroponic, meaning that instead of water being deployed to a stream, it will be provided to a form of a mist. While the idea of aeroponic showers using mist might seem efficient, mist, defined as a thin fog of tiny water droplets, may not be effective for thorough cleaning. Traditional showers with a stream of water are generally more efficient at removing dirt and sweat, especially after physical activity, which, as you know, they will be doing a lot of. The fine droplets in mist may not provide the necessary coverage and pressure to ensure proper hygiene, making an impractical solution for maintaining cleanness on Mars. The statement "gray water" used water from hygiene activities can be treated and reused for non-potable purposes, such as irrigation of plants, lacks an explanation of the actual treatment process. Effective gray water requires several steps: filtering out particles, removing harmful substances through biological or chemical treatments, and also ensuring the water is safe for irrigation, of course. Without detailing these steps, their plan remains incomplete and raises concerns about the practicality and safety of reusing gray water for plant irrigation. At page 12, they state that and they will bring hydrogen, and they also state that nitrogen is necessary, but they do not state nothing about hydrogen tanks, nor how will they procure nitrogen. Will they bring it or tanks as well? They didn't say any details about this. And at page 7, they said that regions like Arcadia Planitia and Deuteroneus Mensae emerge as optimal sites, enhancing the prospects of a suitable and successful Mars settlement. Okay, I understand that regions like this are suitable, but they didn't actually state where exactly they will land and where they will do their research, and basically where they will have their mission. I will pass any other questions to my colleague Edward.
My name is Edward, and I will continue the critiques on TomisMars project. I would like to start by asking how they are gonna establish a communication system with planet Earth. Also, for us especially, we aren't very sure what is your mission and objective, and we cannot make a conclusion in what to ask you. Maybe if you want to make the station independent from planet Earth, how are you gonna make a system in which the suites, the merchant suites, will communicate with the station? Also, I can ask, in what frequency will gonna make that communication? And that's the part for communication. And I will ask also about the part on food, on farming. How are you gonna farm? How are you gonna organize the space, the farm space in which you are gonna farm all the vegetables and plants that you mentioned earlier in the project? So in order to create a supply to feed the crew, also you have to take in mind that every plant has its own growth rate, so it doesn't make any sense. So another question is about the suites. So you mentioned that the materials that the suites will be made are modern materials, but their name aren't mentioned. What materials the suites are gonna be made of? Also, how did you estimate the weight, since the materials that you wanted the suite to be made of, you didn't mention them, so it doesn't really make sense also here. Also, you gave us a sense of wanting to research the planet Mars, but in order to research Mars, you have to send the information back to Earth, but you didn't create a system in which you communicate back to Earth, and also how are you gonna make a plan for this communication system. So yeah, I also said if you want to be independent, how you are gonna make the station independent, because you have to make a more complex plan, since Earth is a big supplier for us, for the station. So in order to make it run, you have to make all the I don't know how to say, all the things run in a cycle, which it won't be affected by the activity on Earth or all the activities besides the activity on Mars. So in order to the people to live there, you have to make a more complex plan to be independent from Earth. Now I will pass my critics on Matei Zăbi.
Yes, I just have some quick things to critique about both of the projects. So first of all, both projects don't really present backup plans for most of the systems. Both projects didn't even take into account that the air on Earth is made only about 20% of oxygen and around 80% of nitrogen. So how will you get the nitrogen on Mars? Because really there isn't a lot of options. So you have to bring it from Earth. If you bring oxygen from Earth, did you take into account the weight of the tanks? Also, the graphics. So on Project Aspera at page 8, how have you estimated the walls to weigh 20 kilograms when there is no visual representation? I don't know how thick they are. How would I know how much they weigh? On Project TomisMars, at the habitat and spacesuit design, the first image, I don't really understand how did you estimate the aeroponics farm to be 120 kilograms? How many towers are they? I don't really understand. Now, about the weight itself, Project TomisMars doesn't really have very good weight estimations, and both projects don't have a total weight estimation. And the graphics, both projects mostly have graphics taken from the internet or some rudimentary graphics without a lot of measurements, a lot of diameters, lengths. There isn't a lot of visual representation of the project. And that's all I have to say. Thank you. I think my colleague Edward wants to add just one last thing.
For both themes, I would like to ask you which is the domain of frequency through which the satellites, the rovers, the settlement, the suites are gonna communicate with planet Earth. The question will be applicable to TomisMars if they intend to communicate with planet Earth. That's all I have to say. Thank you.
Thank you very much for your time and your attention.
Thank you, students, for your well thought out and well prepared critiques of the teams. I do have one comment as far as the bibliography pages. The team that you critiqued did follow the rubric, so you are supposed to provide a bibliography, and that does not count towards the page total of your presentation. So just keep that in mind. Also, when we meet on Friday, please arrive on time and be prepared to start at the top of the hour when we begin. We need to keep this timely in order to be respectful of everyone else's time. I hope the other group shows up for the rebuttals. And if you guys have anything else, please let me know.